Swayam Prabha. Digital India. Educated India.
Work with deep learning model for prediction of dielectric constant, application of reaction kinetics, consideration, solvation effect.
The professor, I'm Swayam Prabha from the University of Technology. It's my honor to give oral report about my research project instead of my supervisor, Liu. Well, our research project is deep learning model for prediction of dielectric constant application to reaction kinetics considering solution effect. Well, first of all, please allow me to give the motivation of my research project. As we all know, the pharmaceutical project industry has brought us the rapid development of the human society. But at the same time, it also causes serious environmental pollution. So, the waste composition is complex. That means the terminal treatment is invalid. But the pharmaceutical production is emphasized from a process-based perspective. Well, the GlaxoSmithKline client report has indicated that 90% of waste is related with solvents. That is to say, the solvent selection is crucial for the production of reaction, crystallization, and other unit operations. In this work, we focus on the reaction solvent. To be specific, is the reaction rate constant. Well, the constant is one of the most important properties for the reaction solvent. Usually, it's calculated as a conventional transition state theory. The theory is a typical method for the calculation of the reaction rate constant, so it can calculate the energy. However, it's also very complex. For the difficulty of the exploration of the transition state limit is fast and wide use. Thus, we want to establish a framework to facilitate the high throughput screening of solvents. So, what's our solution? Well, please allow me to introduce our deep learning-based kinetic model framework. This framework consists of three parts. The first one is the frontier molecular orbital theory-based reaction kinetic model. Well, it correlates the reaction rate constant and the selectivity with the HOMO and LUMO energies and the hydrogen bomb donor and acceptor. Well, the HOMO and LUMO energies are the descriptors of the FMO series, and it can be calculated by the SMD model, which is short for the solution model of density. The solution model of density has a lot of inputs. One of the most important inputs is the dielectric constant. To make it wide and fast use, we establish a deep learning model with multi-vector Morgan frequency descriptor as the descriptor, and use the multi-head extension algorithm and the ensemble learning method to improve the precision of our prediction results. Then I will introduce this kind of things in detail. First of all is the frontier molecular orbital theory. The theory, paired with the transition state theory, provides another insight into the reaction mechanism. Well, it focuses on the descriptions of the molecular orbitals, such as the highest occupied molecular orbital, HOMO, and the lowest unoccupied molecular orbital, LUMO. These two energies, similar to the transition state, will vary with the solvent environment. Thus, we can establish a kinetic model like this to facilitate high throughput screening of reaction solvents. Then we will get the equation 1. However, we have to put the hydrogen bomb donor and acceptor into consideration and change the equation 1 to the equation 2. Well, of course, these two descriptors are important. However, why do we think this change is essential? The software we use is the Gaussian software version 09, and the input has one of the most important input is the dielectric constant, which represents the polar effect of the SND model. Well, let's imagine in this model, the HOMO and the LUMO can be calculated by the dielectric constant and other properties such as the Abraham acidity and the basicity. However, these kind of properties are hard to find, so we have to make some simplification, such as this. Well, we reserve the polar part, which is calculated by SND model with the dielectric constant. However, we made some simplification by just add the hydrogen bond donor and the acceptor into the kinetic model. Well, there are some proofs to demonstrate our hypothesis. It's the figure like this. The red lines are solution HOMO and LUMO energies of asteroids varying with dielectric constant. Well, the blue dots obtained using the comprehensive solvent properties required by the SND model. Well, we can figure that from most of the blue points are in good agreement with the red lines. However, there are 3 dots with extremely high errors. Why this thing happens? After analysis, we find that the solvents mainly because the hydrogen bonding effect. Thus, we found that our hypothesis is feasible. However, the hydrogen bonding effect cannot be neglected. There are also something we have to notice. That is, if we magnify the trend in the right corner, we will find that the error propagation is very big. That is to say, the error when the dielectric constant is below 6 is nearly equal to those which calculate by dielectric constant over 20. Thus, we have to make something to solve this kind of problem. So, our solution is the deep learning model for dielectric constant prediction. The deep learning model uses multi-vector descriptors and temperatures as our descriptors, with multi-added attention algorithm and an ensemble learning method. Well, the latter part is the very well-known transformer model. The model is commonly used for bilingual recognition. However, we don't need to transform a sequence to sequence. We just want to transform a sequence to a result. So we just use this code structure, which is the multi-added attention algorithm. The ensemble learning method, to be specific, is just a method that we will train two kinds of models and use a classification model to decide which kind of model is better when using different data sets. And the multi-vector descriptor is a text-based descriptor. Different from other descriptors, such as the smell string, is more interpretable. That's to say, it can represent the similarity of different segments. Well, with this different machine learning methods, we can make our results accurate and robust. And this is our model result. Well, the next figure is the result of the experimental dielectric constant compared with the predicted value. Well, we use the R-square and the mean-square error as the criteria, and to make some further research, we make some comparison between our tailor-made deep learning model with the deep learning model with the multi-head attention algorithm, but without the ensemble learning method, and the deep learning model without the multi-head attention algorithm and the ensemble learning method, as well as the group contribution-based model. We can see figures from the table that the R-square of our tailor-made deep learning model reached 0.981, outperformed than other models. However, we have to say model with the multi-head station algorithm, but without the ensemble learning method. We are only a little better than it. So, does the ensemble learning method not necessary? Well, we don't think so. To demonstrate it, we make a comparison between the two kinds of models. However, we just use the dialectic constant predicted by these two kinds of models to calculate the HOMO and the LUMO energy. The blue dots are the values calculated by our model, and the red triangles are calculated by the second model. Well, in this figure, we can find that our model can omit the error propagation issues. However, the second model can't. To this end, the ensemble learning method is essential, and our deep learning model method is essential. To further introduce our framework, I will introduce our framework in two case studies. The first one is named the Manchurian reaction. It's also a very well-known reaction in the worldwide. The reactants and the products are shown below. First, we have to select which kind of HOMO and LUMO energy will be our descriptors of our kinetic model. After analysis, we found that the HOMO of the reactant A minus the LUMO of the reactant B is lower than the HOMO B or minus LUMO A. Thus, we choose these two as the descriptors. We also make a comparison of the Pearson coefficient between different descriptors. Although the hydrogen bond donor, the receptor HBD and HBA is important, the HOMO and LUMO is the most important descriptor in our kinetic model. The results are shown below. The first is similar to the third, however, they are different. They are the experimental reaction rate constant compared with the predicted reaction rate constant. The difference are that the first one is calculated by the experimental dielectric constant, while the third one is calculated by the dielectric constant predicted by our deep learning model. The deep learning model results are shown in the second figure, and all of these are about 0.9 in the R-square criteria. So we can say confidently that our model is very accurate. Then we use our framework to screen for optimal solvent and find the molecules like this. However, to our disappointment, we don't find a better solvent. However, although our model not always find optimal solvent with higher reaction rate constant, compared with the non-solvent, it can provide more candidate solvents with properties better than other properties, such as this. Although our optimal solvent is lower reaction rate constant, is less toxicity. It can be seen. Then the second case study, the SNAR reaction. Similar to the Manchurian reaction, however, we have to take the reactivity into consideration. First, we have to find the optimal descriptor, which is in fact the HOMO B and LUMO A. And similar to the Manchurian reaction, HOMO and LUMO energy plays an important role. The results are shown here. The results in the first row are the also substitution and parallel substitution calculated by the experimental dielectric constant, while in the second row are the results calculated by the dielectric constant predicted by our deep learning model. Although this kind of results are not no better than in depth in Manchurian reaction, the R-square criteria are all about 0.8. So we can say it's also very accurate. It's also accurate enough. And with the framework, we find the optimal solvent. For our set, the red stars is the optimal solvent from our work, and the blue stars are reaction solvents from the case studies work. And we can find the selectivity and the reaction rate constant. We will always find the best one, which is to our satisfaction. In conclusion, first, we propose a kinetic model, which is based on the frontier molecular orbital theory. The frontier molecular orbital theory has two descriptors, which is the HOMO and LUMO energies. We use the solution model of density to calculate this kind of thing. But the solution model of density has a lot of descriptors. One of it is most important is the dielectric constant. So we establish a deep learning model for faster prediction of dielectric constant and make it to facilitate the high throughput screening of reaction solvents. Then we will make some prospects. As I have shown above, that the descriptors we use called the word-to-vector descriptor is used based on the Morgan-Brigham fragment. However, the group contribution is also a good method to predict properties. So, based on this, we make a group-based descriptor called the group-to-vector descriptor. It's like this. We make the group to a kind of vector, which can represent the similarity of group vectors and can accelerate the training efficiency of property prediction model and improve the generalization ability. Compared with the word-to-vector descriptor, it can be easily combined with the neural network, such as the graph neural network, attention network, and so on. For the graph, for the group, it is more clear than the Morgan fragment. And that is all of my report. Thanks for the financial support of the National Board and Dalian University of Technology. I'm looking forward to your suggestions. Thank you.
Thank you, Zinwan. Any questions?
Thank you for thank you for a very informative presentation. You are using the Morgan fingerprint, right? If I'm correct.
Actually, we use this kind of text-based descriptor. It's based on the Morgan fragment. However, it first transformed into a kind of vector, where the similar Morgan fragments have the similar vectors that can use to accelerate the training efficiency.
Since if you are using you are using a transformer, so it's a natural language processing model. Can we just use smiles to represent our models, to represent our structure?
Yes, we use kind of transformer, but we don't use all of it. As we all know, the transformer, the input of transformer is a kind of sequence, and the output is also a sequence. And the target of our model is just a result, a property. So we just want to use this kind of. Maybe we will call it a bird and so on. We just use this structure like this. To be honest, it's a multi-atom tension structure. So we use this to establish our framework, and we don't use the whole of the transformer model.
Okay, thank you.
Thank you.
If there are no questions, Thank you, Zinia.